Welcome to BKW Physics. I'm Mr. McConnelly. We're going to talk about the nature of light. So what exactly is light? Believe it or not, there was a pretty big controversy over this at the time it was being discussed. We were talking about 16, 17, 1800s. And Sir Isaac Newton was very respected, had already, put out all Newton's laws, and people really believed in him. He said light's a particle. And he had actual proof, which we're not going to go through today because it's not important that you know that right now, but he had proof and he drew pictures and he had explanations for why light must be a particle, the way it reacted. And he was very respected, and so people obviously thought he was right. Well, there's another guy, Christian Huygens. He's totally unknown. Totally unknown guy. Well, he comes up with this theory that light was a wave, which was really controversial anyway because waves weren't well understood at the time. But he said it's a wave, and he had his own proofs why he believed that it was a wave. Well, both of these proofs seemed to work well, but what finally settled the argument was Thomas Young. Thomas Young came up with a double-slit interference experiment. And basically, I've drawn it out, and let me explain what you're seeing. You're seeing a light bulb here, a light source, and then there's a wall, and that light is allowed to go through a very small, I drew it pretty big, but it's a very small opening in that wall, which would cause it to arc. And what's that arcing called? Diffraction. So it diffracts out, very good, I'm remembering that. Then it gets to another wall that actually has two narrow openings. So this time you have light that's all diffracted already, and it's hitting two more openings, and it will again diffract, but it'll diffract in two separate areas. These areas, though, because of the diffraction patterns, start to overlap one another, and you get in between interference. That's why it's an interference demonstration or interference experiment. Now, if I can hone your attention on these points right here. You have a top, a crest of a wave, and a crest of a wave crossing each other. One came from this side, one came from this side. When you have two crests that are at the same point at the same time, what are you going to get? Two crests, not a crest and a drop. Two crests, two ups. You get constructive interference, you get an even bigger, taller type of thing. Now, what you were thinking of is in between there's a trough. Now where a crest and a trough cross each other, you're going to get destructive interference. It's going to be like what you said, like a no disturbance, because it cancels itself out. And there's also a pattern of those, but I'm not really interested in that right now. I'm worried about where the crest and the crest trough cross each other, and if you trace that out, it actually hits the third wall at this point right here. And the way you see this, if you were doing this demonstration, is there'd be a light source here, and then you would see a bright dot here. There would be some darkness, and then a bright dot here, and etc. It would kind of fan out as a pattern. And this dot is, of course, caused by aligning those crests. Now, if this happened, there's no way you can make this happen with particles, is what Young said. And if this can't happen with particles, hence, light's a wave. This is how he came to the conclusion. He kind of sold the argument. People believed him. Years later, James Clerk Maxwell, you might recall, he's the guy that did a lot of calculus stuff, came up with a lot of calculus. James Clerk Maxwell was a great mathematician. He did a lot of work on this, and he also came up with the idea that light is electricity and magnetism at like 90 degrees to one another, working in combination, the two waves working in combination to produce light. I don't know how he figured it out. The man was real intelligent, and he used a lot of math to prove it. So, most of which, at this point, I would have no understanding if I read it. If I looked at it, I'd be like, yep, okay. I don't know what that means. But moving on. He's a smarter man than I. When we talk about light, so now we've proven light's a wave. Great. Moving on. There are two categories that we need to talk about when you're talking about light. One is coherent and one is incoherent. Now, the incoherent one is the easiest one to understand. Let's focus on that for a second. If the light is just kind of all random, in other words, you got one wave going like this, another wave going like this, another one that's short, another one that's real long, and you combine all those together, and it's just a bunch of light. That's incoherent, because nothing really lines up. The phase has a random phase relationship. Phase, remember, if you're in phase, the crest will align with the crest, the troughs will align with the troughs. But if you're incoherent, it's just random phase. This is like if you had a 40-watt light bulb, the sun, boom, it's just incoherent. The other side of the coin is coherent. This is where the source produces waves that have a constant phase. So you can think of it like they start lining up so that the crests and the troughs are lining up because they have the same frequency. Then everything starts to line up, and that starts to make it coherent. But there's another thing. They're also in the same, they can be in the same plane. So, you know, I could do this, right? And then I could have another wave of the exact same wavelength, like this. See, those, since one's going back and forth and one's going up and down, even though they're in phase, they're not really reacting well with one another. But when you get them in the same plane, so that they're all this at the same time, now you start to get coherent light. A perfect example of this is laser light. Now laser light, people know, like, don't stare at the laser, it hurts your eyes, it's going to damage your eye. The reason is because it's coherent, all the crests are lining up, that is making super intense constructive interference, so when that light goes into your eye, it's intensified compared to a normal incoherent source, and it actually can, you know, burn in your eye. And that can be used to correct your vision if you go get laser surgery. It can also be used to damage your eye if you just randomly shine it in your eye and you're not paying attention to what you're doing, you don't know what you're doing. But what most people don't know is that laser is an acronym. It stands for light amplification, stimulated emission radiation. Most people just hear laser, they're like, yep, that's a word, I know what it means, it's one of those lights you can shine a long distance. It actually means this. One last thing before we close this up is coherent light sources. The packets of light that are produced, think of it like a packet of light, are quantized, or they're in quanta, they're in packets. And that word quanta comes back quite a few times in physics, like quantum mechanics, quanta. And it's just the first time we've maybe seen it. So for today, that's our summary of light.